Hey class, it's just me, Mr. Wee. I just want to go over 5-3 in a few different parts, but it's just basically talking about when you find f prime, f double prime, and you compare it with the original graph of your equation, f, basically, okay? So the first thing we're actually going to talk about is what's called the first derivative test for local extrema. As a review, these are local extrema, meaning like we're looking at minimums, maximums, like whether they're local minimums, like they're just like locally the max point, or there's just if you cut off the interval from like maybe C2 and C4 here, then you know that C3 at C3, like x equals C3, the local minimum value would be 0, or the local minimum value would be right here, meaning the slope is 0 right there. So we're going to find out how to solve for these just using the first derivative of your function, okay? Meaning that you just find the derivative of your function, your equation, okay? So here are the steps that you want to write down. So you can take a minute to just pause this and write this down if you want. Let's see if I can get that out of the way. There you are. Okay, so it's first derivative for test for local extrema. Let me just go through it. You can pause it and then try to go over it on your own, and then try to come back with to figure out what I'm saying. Find the derivative of your function. It's really simple. So if you had f of x equals x squared, you want to find the derivative, 2x to the first power, let's say. That's a very easy example, okay? You want to find the derivative function for your function. Next point is you want to set your derivative function equal to 0, because basically we're trying to find out where your where your graphs are kind of like leveling out and changing. So watch, like from here, you see how it's like, oh, look at the slopes. It's increasing. It's a positive slope. And then it just kind of teeters off and becomes flat. That's a slope that's flat. That's a slope of 0, and then it just keeps going down negatively, okay? That would indicate to you that you might have a local max, but we need to find out where the derivative is 0, right? Like which x value. So that's what you're doing right here for step 2, okay? So you might find in the book that they call these critical points, and also look at your endpoints too. So I said that maybe if you're given like an interval, so sometimes you might be given the equation f of x, but then you might be given this restriction, like we're only looking at this function from like 2 different x points. So here you can kind of see, that this crazy function is actually cut off at x points. They call them b and a. They could be any points that you can think of, but that's where it stopped, right? And between here and here, we might actually find out that, look, one of the endpoints actually ended up being an extreme point. It's an absolute minimum. And here we call this to be a local minimum, because if you stop the region right here, like if you stop like even here and here, no, I wouldn't say that. Like if you make the interval from x equals c4 to like x equals b, the endpoint ended up being the local minimum. So you can't discount the endpoints. So you can't just find out where the slopes are equal to 0, at which x values the slopes are equal to 0, but also where the endpoints are. We got to test them out and kind of see any trends for or we have to kind of see anything about the endpoints to see if they ended up being minimum values or maximum values, okay? As well as that, there are different cases where we call them no extremes. You'll see what this means. It could be a place where there's an f of x that's actually equal to 0, like there could, or the derivative of that point, or that slope at that point, is that might be equal to 0, but it might not be considered anything. Because look, if you look at this and you try cutting it off, right? It's like, what is that really? Like even if I put it in an interval, it's not a local minimum or maximum. So they just call those no extremes. And then you might actually have a point where it's an absolute maximum, right? But the slope is actually undefined. The reason why this one is considered undefined, because look, it doesn't approach 0. I wouldn't call that a slope of 0, but what do you call that a slope of? Because from the left side, it approaches sort of like a really high number, and then the right side, it's not gradual at all. It just abruptly goes. That's not a slope of 0. This is definitely a slope of 0. It's like definitely approaching like, oh, this is positive 1, or this is like this is a slope positive 5, and then as we get closer, it's getting steeper, and then all of a sudden towards here, it like gets a little bit a little bit more slopey, and then all of a sudden it just stops here at 0, and then it gradually increases or decreases a lot more. Like it could be like a -1 slope, -2 slope, -3 slope, and then -4 or 5 slope. You know what I mean? It's gradual. It approaches 0. Here you can't do that. It's just like it just goes up and then just comes down. What? That is an undefined slope. Okay. We'll get more in detail into this. I'm just giving you the basic steps. So basically, find the derivative function of your function, and then not plug it in, but like set it equal to 0 and find out the x values that make it 0 or make it undefined. You can even say fx, like where is it considered undefined, right? It's not that bad. It's not as hard as it sounds right now. And then what you want to do is you want to look at, like, this is a number line for each critical value. So imagine I found all my critical values, all my x values that are critical or my endpoints. I set them on a number line, and then I look and I plug in x values into the derivative, and then see if, like, around it, if it's like positive or negative slope values, or is it negative. You'll see why that's important in just 2 seconds. And then from this here, if you find out if the slopes are negative and positive around your critical values, you can determine if those x values are like an absolute minimum, are an absolute maximum, are they local minimums, by not even looking at your graph. You don't even have to look at your graph. You just look at what the slopes are around these critical x values, and then you can just determine it from that. So this is what I mean. Okay, so we're done with the steps. This is what I mean. Let's say, let me see if I can back this up. Here's one scenario. This is actually in your book on page 211. You can actually look at it yourself. Let's look at the x value. Or like, let's say that we got our derivative function, and then we set it equal to 0, or we just find out where the x values, and we set it equal to 0 to find out x values where the derivative is 0, or we find out the x values where they might be undefined, and so forth. Here, check it out. I put it on a number line, right? And then I found out that at c or whatever x value, the slope is equal to 0. And then I just test like another x value around that. And I plug it into the derivative function. And if it's positive, and then like to the right of it, I plugged in another x value into the derivative, and I saw that it was negative, like negative going, or positive going to a negative. That might be a local maximum value. Okay, so this is a nice image saying that if you test out some numbers here and you find out your slopes around here are positive, and then it hits that critical value and then it goes to negative, you possibly got a local max. Most likely you have a local max. This is also a scenario where your x value, if you plug it into your derivative function, you get an undefined answer. But same case, if your slope goes from positive and then hits that critical value, and then any point to the right of that is a negative slope, that also tells you have a local max. I'll play around for some more scenarios that are actually in your book. You can read it yourself. But opposite of that is, if let's say you find that x equals c is a critical value, and then you test out a point to the left and the right, and you find out the slope on the left-hand side is negative, it's less than 0. But then you find out the derivative value here to the right is positive, negative, basically, all right, I didn't do this, okay? Negative going to positive, basically. Negative going to positive. That should tell you that you got a local min, okay? Here, however, is insane. What if you had that you find around your critical value, you test out 2 points around your critical value and plug it into your derivative function, that they have the same sign? That's where you get this no extreme. I mean, technically, the slope is 0, but that doesn't necessarily mean it's a min or max. It could just have no extreme. Here, it's what if your f of x is equal to undefined, like x equals x, x equals c, like x equals whatever it is, and whatever this point is, if you plug it into the derivative function, you get an undefined answer. I mean, it doesn't necessarily have to be negative. The point is, if you plug in slopes numbers, like x values, into the derivative function onto the left and right, and they both have the same sign, you don't have an extreme, okay? And then here's the case with the endpoints. So the endpoints are a lot easier. If you know it's an endpoint that's like to the left, like the left endpoint of the graph, and then you just put in like an x value into the derivative function that's like, and then you see that it's negative, then most likely you have and if it's negative, most likely your critical value is at the end of that, at the end of that string. So that tells you that it's the local max. Okay, so just study these last two. I'm not going to go over it, but this just tells you that the endpoints are also very important. Okay, guys, that's all I'm going to go over for the first part, and then I'm going to go over an example problem in the next one. Okay, thank you. Bye.